It is the wee hours of the night, and I wasn't going to do this, but I got through a practice run surprisingly quickly, so hopefully this will be a short one. Let's do balanced binary tree. Given a binary tree, determine if it is height balanced. I got this highlight. A height balanced binary tree is a binary tree in which the depth of the two subtrees of every node never differ by more than one. Okay, so I was originally going back and forth on whether I wanted to try to do breadth first search or depth first search. So let's talk through what the decision there is. In breadth first search, you could do say row by row traversal. Say go row here, you go here, and then at each like additional frontier, you compare maybe the size of each one. Okay, so how would that work? If you want it to be balanced, let's look at this counter example here, which is not balanced. Okay, so at the first level, you expect there to be one. Now you can get away with having like, maybe this child doesn't exist and this one does, as long as this one doesn't have any children of its own. So it'd have to be, does one child, do both children exist, or does only one child that exists and it itself has no children? So that is an option. You could do that, and maybe there's a couple finicky ways you could do it. You could either look at like at each step, you look at itself, and the work is looking at how many children each of the children has. So you'd say like, okay, we're visit pop one off the queue, and we visit it. Now the work of doing that is first, we're going to add its children to the queue, obviously. And when we're adding those children, we also look at the number of children they have and say, okay, there'd be an if conditional. Do they both exist, or does only one exist and the remaining one has no children? So that's an option. I think that would work. Uh, that one I think is conceptually simpler, but a little harder to implement. So with depth first search, what you could instead do is get the maximum depth below each of the children. So starting at, one, what is the max depth below its left child, to the left, and what's the max depth to the right? So you do it'd be a recursive call. And as I usually say, recursive functions are in an interview setting very nice because they're conceptually like a good thing to show off, and they're a little bit faster to write and implement as long as you can deal with the logic. In a production setting, you generally don't want to use recursion because they do not scale well, even if like mathematically they're fine. You hit stack frames and the actual implementation on the machine. There's limits to how far programs are willing to recurse that the operating system will even let them recurse. But in an interview, they're cool. So you'd say, okay, what is the max depth below 2? Well, you'd theoretically get back, going to the left, you'd get 1, 2, 3 back there, and you get 1 back here. Okay, 3 and 2 and 1, the difference between those is more than 1. So you'd return false. And let's go ahead and start writing that out, actually. So with recursive calls, another thing I usually recommend is, okay, you're given this function signature that you have to adhere to usually. You've got ultimately you want to output something in particular, and you get some particular inputs, and you can't change those. So I think it's honestly usually just it's better to write two very similar functions. One is like the one that does most of the work, and it has the signature that you want. So in this case, it'd be checking the max depth. So int max depth, and it takes 3 node pointers. Yeah, so very similar. They're going to do similar things, but the point is to just set up the inputs and kick off this, and then it takes the output into the format you want. And it's safer, and it's safer to the point where it's usually going to save you time, even though it's a little bit redundant. All right, so when we have pointer inputs, obviously always check for null pointers. And then, and like in this one in particular, it's also recursive, so you need a base case in addition to that. All right, let's start off with the edge case check. So if not root, if it's null, what do we return? Well, if there's no root, actually that is going to be balanced. It's got no children. That's balanced. So return true. And then do we care for one? Yeah, I think that takes care of that. And in this one, if not node, return 0. It's going to have a max depth of 0 because it itself doesn't even exist. What are we going to do? Okay. Let's think about what we're doing here. So if, not if, we're going to int left equals max. We're calling on the left and right children here. So max depth node left int right max depth node right. Return 1 plus the max of those two. And we need to do some additional work to set our output. So how are we keeping track of that? Ultimately, we want to return a Boolean. And we're doing all these crazy recursive calls. So the way you'd either deal with that is instead of returning an int, you return some compound structure that you create, a class or struct or a tuple or something. And then in each recursive step, you're like comparing what you got back from the previous versus what your current calculations are. Um, in this case, and it's often the case, in these kind of like easier difficulty problems, it is marked as easy on LeetCode. Just make it global. It makes it, you can't parallelize if you use globals. It's not, okay, it's not global, it's class wide, but in ret, sorry, it's Boolean. And I'm initialize it, I guess, to true. When you have like a shared individual value like this, you can't parallelize it at all because you're checking the value of it at every stage. You might modify it at any time. Um, but unless you're doing specifically like a parallel problem, which you might, I've kind of I had an interview once that was on external sort, which you can parallelize. That was specifically for like an embedded role. I didn't get the offer, spoiler, but that wasn't for lack of trying, uh, and it was because of head count drops in the middle of last year. So I actually did make it past the interview stage and go on to team matching. But that is neither here nor there. We're using a global. It makes it hard to parallelize, but it's conceptually easier. And I'm initializing it to true because realistically, the goal would be, okay, we're doing some like a bunch of scanning. We're scanning through this tree, doing depth first search, and then we're just looking for defects. And if we ever find a defect, then we set it to false, and then we can gain back some real world runtime, even if not theoretical runtime, by exiting early once we know that, okay, it's no longer the case. But the worst case scenario is always going to be it's true. We have to scan through the whole tree and we find nothing wrong with it. So that's why I'm initializing it to true. And then, so that means we've got this. And now I can do like the work of comparing if at any particular subtree is that balanced. So if absolute value of left minus right, if the difference is greater than 1, we set our output to false. And then in order to get back that actual real world runtime, like I just mentioned, I'm going to add an additional case to our exit condition, if not ret. And we've set ret to false. We're not even going to bother. And it doesn't, once it's false, it does not matter what this output is, because we're never going to like set it back to true. So we go ahead and return early. So this is our recursive call. We've got our, kind of an exit condition. We've got our base case. This as opposed to an edge case, which is on our main input. And then let's go ahead and set up this and kick it off. So int left equals max depth, root left, and the right side. And then we're going to do the same comparison. If abs left and right greater than 1, return equals false. And that should do it. Before I forget, let's talk about bounds and do an example. All right, it's going to be O of n time and space. And it's depth first search, so that's the classic runtime of it, but it's a tree, so it's not like O of n plus m or O of like v plus e, as you might see sometimes. It's the number of edges and the number of nodes are very similar. They're always on the same order, so it's just O of n, where n is the number of vertices or the number of edges. It doesn't matter. And then space, because even though it's hidden, it's recursive, you still have call stacks. You could end up having, suppose we've got this early exit, so we're probably not. Let me think. Would we have the entire tree on a stack? Like, okay, if there's a single node, then yeah, we could have the entire tree on our stack. Um, so if it's a line, if something like this, we are getting the max depth of the left first. And that is, we've got this exit condition, but we never set this exit condition until we check the right. So yes, we are going to go down the whole left. So suppose all this existed and this didn't exist, you'd have the whole tree in stack frame. So that is linear space. All right, let's do an example. And I should mention that you cannot do better than this, because ultimately you're gonna scan the whole tree. Okay, you're gonna have, if it is a balanced tree, you're gonna have logarithmic space. No, because you need the entire one side. It's depth first search for sure, which is I gotta think about, can you do better? Not really. Mainly it depends on the, okay. These false cases are always gonna be a little bit worse than, okay. True cases are gonna be the worst for runtime because you have to scan through the whole tree. You're never gonna exit early. False cases are better for runtime, but worse for space. Are they? Yeah, they are, because you have more of the tree in the length versus if it's balanced, you have the tree more spread out across the different sides. So you'd only have like the logarithmic stack frames before you return from that. Yeah. So true cases are going to be logarithmic space, but O of n time. False cases are up to, well, linear time and space. Anyway, that's probably a little bit egregious on the detail. Let's do the example. So we've got our stack. Go ahead and write that out, and we've got a return value. Alrighty. I'm gonna go ahead and do, I guess this exam. I'll try and run through it quickly. So this one first. We're just true, left. Okay, we're gonna go left, and so we're starting on max depth. So we'll go stack frame. Okay, yep. So we start off with 9. No, we're at 3, and then we go to 9. There's no children there, so it's going to get zeros back from its children. 0 minus 0, that's okay, that's not going to happen. So now it's going to go to the right child. So then pop that off, and then we go to 20. We go to its left, and then that's going to get zeros back from its children. So it's going to return 0 minus 0. Sorry, that's not going to set the thing. It's going to go 1 plus the max of 0 or 0. So it's going to get 20 is get a 1 back from 15, and now it's going to go to 7. So 15, and then take that off, and then now we're 7. The same thing, so it's gonna 7 is gonna return 1 to 20. So 20 is gonna get back 1 from both of those. So it's not gonna set this, and it's gonna return 2 back to the 3. So 3 has got 2 from 20, and it's got 1 from 9. And it's gonna compare those. So 1, 20, sorry, 1, 2. Those differences are within 1, so that's not gonna be the case, and it's gonna return true. All right. Now let's look at the counter example. Start off with 1. It's going to recurse on its left child. That's going to curse on its left child. That's going to curse on this left child. So 2, 3, 4. 4 is going to get back zeros from its null children, and it's going to return 1 back to 3. So 3 just got 1 back, and it's going to recurse on the other 4. And the same thing, it's going to get 1 back from 4 is going to get 1 back. It's going to return 1. 3 is going to have 1 and 1, and so it's going to return 2 back to 2. So 2 has now gotten 2 from the left. And now let's calculate the right. It's going to go to this 3, the right hand 3. And that's going to get back 0s from its null children, and it's going to return 1 to 2. So 2 is now looking at that. And I think that's fine. So like, it has 2 children, so it's okay if one of its children has children. And now it's going to return 1 plus the max of 1 and 2, so it's going to return 3 back to this 1. So 1 got 3 from the left. So now let's calculate its right child's max depth. We're looking at that right hand too. It's got new null children, so it's going to get zeros back from those, and then it's going to return 1 back to this 1. So it's going to get 3 and 1. So this is where something's happening. And we're dealing with the root, so we are back to here, I think. Let's see. This is balanced. We're expecting this to be balanced. So yeah, this 1 is really where the imbalance is introduced, because that's too many layers. It's got, yeah. So this has, yeah, okay. It is here. This is the first one that's what we're expecting. So we're back in this function here. We just came out of here. And now we're comparing 3 and 1. So 3 minus 1, that's 2. That is greater than 1. And so we're going to set our output to false, and we're going to return false. That's what we expect. So I'm going to go ahead and give that a run for syntax, because I think that's everything. No, what I say? Node left, max depth. Oh yeah, typo. Depth with a TH. Cool. All right, accepted. And go ahead and submit. Nice. And then mark it off. Thanks and good night.